Welcome to the lecture series on numerical methods. In the last lecture, we have discussed Newton's forward difference formula and Newton's backward difference formula. In the present lecture, we will start about this error computation for Newton's forward difference formula and Newton's backward difference formula. So, before going to the Newton's forward difference formula error computation, first we will just go for this Newton's forward difference formula's representation. So, how we are just representing the Newton's forward difference formula is that first we can just write this one as y of x or y of xp for a particular point usually, or as yp as a function of p. We can just write this one as y0 plus p delta of y0 p into p minus 1 by factorial 2 del square of y0 plus up to the term like p into p minus 1 up to p minus n minus 1 whole divided by n factorial del to the power n of y0. So, especially it is in the form of p, we are just writing this one, and if we will just write in terms of x, then we can just write y of x as y0. So, p can be expressed in the form of x, that is nothing but x minus x0 by h delta of y0 plus x minus x0 by h x minus x1 by h 1 by 2 factorial delta square of y0 plus up to the last term. So, specifically if you will just note this notations here, the first formulation we can just apply if a value is asked to compute at a particular point, that where we can just determine the value of p and we can just apply that formulation to evaluate this function at that point. But if this function is asked to compute in the form of a polynomial, then this second formulation we can just use there. So, if you will just see in the slides here, that is y of x is expressed in the form of y of 0 plus x minus x0 del of y0 by h plus x minus x0 x minus x1 del square y0 by 2 factorial h square, and the last term especially it is just expressed in the form of x minus x0 x minus x1 to x minus xn into del to the power n of y0 by n factorial h to the power n here. And before going to use this formula, first we should have to note few points, that where you can use this Newton's forward difference formula or where we can just use Newton's backward difference formula or other forms of this finite difference operators formulas. So, first if you will just go for this application of this Newton's forward difference formula here. So, this formula can be used to compute the value of y for a given value of x, and the formula in terms of x, it can be used for this representation of this function y as in the form of a polynomial here. And then in the second form, if you will just say that as many differences we can just try to retain without losing its accuracy, we can just put there. And in Newton's forward difference formula, especially the number of differences for a particular y decreases as we go downwards the table, if you will just see. And if we want to find the value at the beginning of the table, especially this formula is the suitable formulation to evaluate these values at the beginning of the table or at the start of the table there itself, or in the upper end of the table there. So, there are other formulas which can be you can just use for the computation of the values near the middle or end of the table. And if sometimes we are just observing that these differences start behaving erratically or increasing in magnitude at any stage, we should leave out those differences and higher order differences of this formulation. This means that suppose if you are just going for this computation and after suppose second order differences, if you will just find that the third order difference values is getting increased or it is just infinitely getting is increased off, then we can just terminate this series up to second degree term here and we can just evaluate these values there itself. And sometimes suppose if the starting point is not the origin, then we can just shift this origin to the immediate next point. If you will just consider these points like your starting points are x0, x1, x2, x3. So, likewise if the points are existing here and suppose if the value is asked to compute exactly at x0 or within this interval x0 to x1, then you can just use this Newton's forward difference formula. But sometimes if the value is lying between suppose x1 to x2, you can just switch this x0 position to x1 here, then your tabular value will be shifted like x of minus 1, x0, x1, x2 up to xn minus 1 here. And sometimes also if this value is asked to compute within this interval x1 to x2, then again also you can just switch these points as x of minus 2, x of minus 1, x0 to x of n minus 2 here. And if you are just shifting this origin according to your choice, that where you want to evaluate these values or which interval you want to evaluate these values or the value is asked to evaluate, then in that interval you can just find that p should be lies between 0 and 1 here, since especially you are just expressing xp or x as x0 plus ph here. So, that is why whatever this point, if the interval is lying between x1 to x2 here, then you can just consider this point as like x of like 1 and 2, within that it will just exist. So, that is why you can just consider x minus x0 by h as p there, and if we are just considering this x0 as the immediate previous point to the next point and where we want to evaluate these values of p there. So, that is why we can just say that p should be lies between 0 and 1 there, and Newton's forward difference formula can be applicable. And sometimes for the extrapolation before the first tabular point, p will give the negative values. To find the error formula in a combined form or in a commuted form by replacing y equals to f of x by means of a polynomial p of x, especially here what we are doing is, if the tabular values is known to us and if the complete function is not known to us, then especially we are just evaluating this function by considering all of these tabular points. So, if we are just approximating this function with this polynomial, then the error will exist there itself. And if this error is existing there, then if you will just take this difference like y of x minus p of x, then this represents the error term at that position. So, especially this can be written in the form of like x minus x0, x minus x1 up to x minus xk into f to the power k plus 1 zeta by k plus 1 factorial, where zeta should be lies between x0 to xk here. And sometimes also in a product form, if you want to express, this can be written in the form of like product of I equals to, or you can just say that n equals to 1 to k there, especially if you want to write in the form of I here, I equals to 0 to k, and we can just write this one as x minus xi, and obviously we can just write this one as f to the power k plus 1 zeta by k plus 1 factorial here. Where zeta should be lies between x0 to xk, and to get suppose this f of x in a differential form. Differential form means how we can just express f of x in terms of f to the power k plus 1 term there. Then to get that form, we have to expand f at points suppose like x0, suppose if we want to expand like f of x0 plus h, since usually this Taylor series expansion is used if a point is given and all of its neighborhood points, if f is continuous, then we can just use this Taylor series expansion that is in the form of f of x0 plus h, which can be written as f of x0 plus h f dash of x0 plus h square by 2 factorial f double dash of x0 plus all other terms. If we will just go for this computation of this f of x in terms of f to the power k plus 1 term here, so then we can just use this mean value theorem for all other terms there. This means that we can just write f of x0 plus h minus f of x0 as h f dash of x0 plus theta 1 h here by using mean value theorem. Mean value theorem, where theta 1 should be lies between 0 and 1 there itself. So obviously we can just write this f of x0 plus h minus f of x0 as del f of x0. This equals to h f dash of x0 plus theta 1 h here. If you will just repeatedly apply, then we can just write del square of f of x0 as, we can just write this one since it is expressed in the form of like h f dash of x0 plus theta 1 here. So then it can be written as h square f double dash of x0 plus theta 1 h plus theta dash h here, and directly we can just say that theta dash should be lies between 0 and 1 here, and we can just rewrite this formulation as h square f double dash of x0 plus theta 1 plus theta dash into h this one, where theta 1 plus theta dash, if you will just see here, so theta 1 is lying between 0 and 1, theta dash is lying between 0 and 1 here. So that is why we can just say that theta 1 plus theta dash should be lies between 0 and 2 here. And if you will just write another parameter, suppose theta 2 here, and which can be expressed as theta 1 plus theta dash by 2, then we can just say that theta 2 should be lies between 0 and 1 here. So obviously we can just rewrite this formulation in the form of like del square of f of x0 as h square f double dash of x0 plus this is 2 theta 2 into h here, and successively if you will just use this formulation here repeated way, then after like a kth steps we can just obtain this one repeatedly. Suppose this forward difference operator we are just using here, then we can just write theta to the power delta to the power k f of x0, this equals to h to the power k f to the power k x0 plus k theta k h here, where theta k should be lies between 0 and 1 here, where f of k, especially it is called kth derivative of f of x, and it may be noted that since theta k is lying between 0 and 1 here, obviously we can just determine the exact value of like this point x0 plus k theta k into h, exactly what it is just giving the providing the value whenever theta k equals to 0 and theta k equals to 1 there itself. So if we can just determine, then we can just write it in a composite form there, and if you will just write in this form, then we can just write del to the power k f of x0 as h to the power k f to the power k of zeta here, and if we want to find the range of zeta here, then if you will just put here like theta k equals to 0 suppose, then this value like x0 plus k into theta k h, this will just give you the values as x0 here, and if you will just put theta k equals to 1 here, then we can just say that the value of x0 plus k into theta k h, this is nothing but x0 plus k h, that is nothing but xk here. So that is why we can just say that if we can just express delta to the power k f of x0 in the form of h to the power k f to the power k of zeta, then zeta should be lies between like x0 to xk here. So, these things you can just clearly visualize here also, that if x0 plus theta k into k h should lies between x0 to xk, then generally it may be written as delta to the power k of f of x0, this equals to h to the power k f to the power k of zeta, zeta should be lies between x0 to xk here. And further, if we will just go for this like forward difference formula, if it is just passing through these points like xi yi, where xi are the nodal points and yi are the associated functional values, then we can just express this remainder term as, if you will just see here, the error term r of x is usually written in the form of x minus x0, x minus x1 up to x minus xk f to the power k plus 1 zeta by k plus 1 factorial here, where zeta should be lies between x0 to xk here. And if we want to represent in terms of like Newton's forward difference operator here, then we can just write this one as x minus x0, x minus x1 to x minus xk into del to the power k plus 1 y0 or f of x0 we can just say, by k plus 1 factorial into h to the power k plus 1 here. So, this is the generalized error estimation formula for Newton's forward difference formula here. So, if you will just use this transformation, that is like we have already shown that if we will just write like p minus I, this can be represented in the form of x minus xi by h. Since already we have shown that p can be represented as x minus x0 by h, that we have just expressed in the beginning, since x equals to x0 plus ph. So, that is why we can just write p equals to x minus x0 by h, and if we will just write like p minus 1, so especially it is represented in the form of x minus x1 by h. So, likewise if you just express p minus I can be expressed as x minus xi by h here, and in terms of p, if you will just write this error formulation, then r of p can be written as p into p minus 1 up to p minus k del to the power k plus 1 y0 divided by k plus 1 factorial here. And it may be noted that if all the tabular points like x0, x1 to xk approaches to x0, suppose if h is very small, then we can just say that del to the power k of f of x0, this can be written as h to the power k f to the power k of x0 here, for k equals to 0, 1, 2 up to any values you can just say. For a small h, we can just write this formulation as in this form here. Then in that case, this truncation error reduces to r to the r of k plus 1 x as x minus x0 whole to the power k plus 1 by k plus 1 factorial f to the power k plus 1 zeta, where zeta should be lies between x0 to xk here. So, if you will just go for this error estimation in terms of Newton's backward difference formula, then this error formula or error committed is obtained by replacing this function y equals to f of x with the polynomial p of x as y of x minus p of x as x minus x0, x minus x1 up to x minus xk f to the power k plus 1 zeta by k plus 1 factorial here, where zeta should be lies between x0 to xk there itself also. And in the product form, as we have expressed in the earlier section, that usually it can be expressed in the form of like product of x minus xi f to the power k plus 1 zeta by k plus 1 factorial, where zeta should be lies between x0 to xk here. And if you just substitute here, that is p equals to x minus xk, since we are just starting this backward difference formula at the end of the table. So, that is why we can just say that the last point as xk there itself. So, that is why p can be written in the form of x minus xk by h here, where we can just write x equals to xk plus ph here, and your r of x or the remainder term can be written as r of x equals to y of x minus p of x, as sometimes usually it is written as f of x minus px, since y of x is approximated by this function f of x there. And if you just substitute all these values, then we can just get this Newton's backward difference formula error as r of p. This is the error term for Newton's backward difference formula, and it can be expressed in the form of like p into p plus 1 into p plus 2 up to p plus k, and this can be written as h to the power k plus 1 f to the power k plus 1 zeta divided by k plus 1 factorial here, where zeta should be lies between x0 to xk here also. And if we want to represent it in Newton's forward difference formula form, since usually this error is represented in the form of Newton's forward difference operator. So, if you will just represent this formulation in terms of Newton's forward difference formula, so it can be written in the form of like p plus 2 up to p into p plus 1 into p plus 2 up to p plus k. Then the next term it will be del to the power k plus 1 f to the power, we can just say f of zeta here, divided by k plus 1 factorial, and where zeta should be lies between x0 to xk here also. Since already we have obtained that h to the power k plus 1 f to the power k plus 1 x, this can be represented as a del to the power k plus 1 f of x here, where x is lying between x0 to xk. Then if you will just write all these tabular points which is approximating towards the point xk for small h, if xk is approaching towards x0 x1 to xk, suppose xk minus 1 here suppose, then we can just say that rk plus 1 of x here, this can be represented as x minus xk whole to the power k plus 1 divided by k plus 1 factorial here, and f to the power k plus 1 zeta, where zeta should be lies between x0 to xk here. Especially if you will just see here, we are just saying that all of these points just it is tended by this point xk here. This means that xk is tending towards x0, xk is tending towards x1, then xk is tending towards xk minus 1 there. So, that is why this formulation for a small h can be reduced in this form here. So, thank you for listening this lecture.